started. So here we are. Okay, this is recording, and thanks for being here, everyone. If for those who are watching online, there's an incredible crowd here. The place is packed. Couldn't believe it. There's almost no room to sit. I'd show you, but I can't turn the camera around. So I'm going to go ahead and start sharing the screen here. Start. There we go. Today we're talking about climate models. We see a lot of climate models this quarter, and the outputs from climate models, and we use them a lot of different ways. So we'll take part of this morning to talk about climate models and how they work. I think I'll sit, and that way I won't wander away from the microphone. So for example, we see often many kinds of graphics like the one shown here. And I'll use the computer pointer so that this gets recorded rather than the laser. So what we're looking at here is different parts of the world. These are temperature anomaly graphs for global scenarios of temperature or of warming in the future, and calibrated for known data. Okay, so we can ask, how do weather and climate work? And we can use climate models to help figure that out. Then we can take those kinds of, that kind of understanding and ask what if questions about how weather and climate will work in the future with an atmosphere that has a whole bunch of greenhouse gases and that's warmer. So this graphic here shows weather data and climate model simulations of past data. So you take known data, which we have from the instrumented record, and you put it into the climate models, and then you ask the climate models to recreate the known data, and you basically calibrate them. Does the model recreate the known data in a high fidelity manner? If the climate model operates, or the climate model output is different from what the historic data say, then there's something wrong with your model, because the model should be able to, if it's working properly, should be able to recreate the historic data. Once it does, sometimes models take a little bit of fine tuning. Once they do recreate the historic data, then you can ask questions with that. So you can take the model then and spin it out to the future, and we'll see an example of that in a moment. Or you can ask what if questions, like in this case, these graphs show what would the warming look like if the anthropogenic greenhouse gases were absent. Okay, so the data are in the thick black lines, and the computer models put out predictions or scenarios of climate that are portrayed by the pink bar. And so you notice that in all these various subregions of the globe, that the pink bars pretty much match the pathway of the thick black line, suggesting that the climate models reconstruct the historic data pretty well. So it's the overlap of the thick black line with the pink bars that show that the climate models are operating pretty well. The observations fit the models. So now you can go into the model and remove the greenhouse gases, and we'll talk about how these models are constructed in a little bit. But you tell the computer model, you go in and you adjust the concentration of greenhouse gases in the program, and that's what's portrayed by the blue bars in these graphs. It shows what would temperature on Earth have looked like if there were no human anthropogenic forcings due to greenhouse gases or land use change. And you see that the temperatures, that those blue bars are somewhat horizontal, suggesting that there would not have been this uptick in warming shown by the pink or the black bars, and things would have stayed, it's kind of steady. shown by the blue bars. And this graphic shows some really interesting ways of looking at this for the entire globe right here, or the global terrestrial surface, or the global ocean surface. So this is borne out both on land and over the oceans. Now on land, we see that the warming is higher than over the oceans. And one of your classmates actually sent me an email question about this from the last lecture, asking about why the warming on land might be greater than the warming over the ocean. And let's just hold off on discussing that for now, but let's get back to it next week when we're all back together again. And again, the model shows that if you further parse these out, the global land graph into these 6 regions, then the trends are the same. You get the observations and the reconstruction in pink all tip upwards, whereas the model outputs with the lack of human forcings are kind of stable over time, shown by the blue bars for each of the continental regions. So that's one way you can use a computer model. You're basically doing an experiment using the model by tinkering with some of the numbers that are in the model. Here's another kind of way that climate models can be used. We said that once you're confident that your climate model reconstructs the past in a manner that you're confident in, then you can use it to spin it out into the future. Okay, this is kind of used in the climate model like a crystal ball. Notice the image on the very first slide was a crystal ball, because these global climate models, GCMs, and you'll see that abbreviation in the book and in lots of slides, GCMs. Sometimes some people take that to mean general circulation model or global climate model. In any case, one of the ways that they're used, probably the majority of the way they're used, is to try to determine what things will be like in the future in various places. Okay, so here's one portrayal of this kind of a scenario. Change in precipitation by the end of the 21st century. Inches of liquid water per year. Okay, let me move this little thing here. So the color-coded graphic legend over on the right-hand side shows that the dark blue colors indicate wetter conditions and the brown colors indicate drier conditions. Notice that in North America, for example, the Northeast is expected by at least this particular projection to become wetter by maybe, I don't know, 6 to 10 inches per year, maybe. Much of the Midwest or the southern Midwest, the Plains region getting drier, notably California drier, okay? We see some regions getting quite a bit wetter, other large regions getting drier, like this large expanse of Brazil, for example, and some of the parts of Africa where there's tropical rainforest still exists, so that'll be stressed out. We've got the sub-Saharan region, the Sahel, where they are often the food security in that region is challenged by drought. But notice how I said that this is one projection, and the outcomes of these kinds of scenarios, that's another word that's used often, is scenario, is it all depends, of course, on the boundary conditions or the conditions that you input into the model to begin with. It also depends on what the baseline is, the years that it's compared to, and it depends on what time horizon in the future it's supposed to be. So let's see, what does it say? Change in precipitation by end of 21st century. Okay, and then here's our units, inches of liquid water per year, and that's the colored bar over here on this side. And over here, it tells us where it came from. It doesn't tell us the baseline years. But as I've said before, often with these kinds of maps, if it doesn't say, then a fairly safe assumption is that the baseline period is 1961 to 1990. A good graphic will have that information embedded on there so that you don't have to make that assumption. Okay, here's another way that climate models can be used. They're not simply about how geophysical or earth science processes work or how the biosphere contributes, but we could also incorporate various kinds of social or economic factors into the outputs or the scenarios that these things generate. And that's what this graphic shows us. So over on the left-hand side is this timeline going from 1900 to 2100. So, and then on the y-axis is global surface warming in degrees Celsius. So it's an anomaly graph. There's a 0 point there. So it's using as the zero basis sometime here before the year 2000. Again, it might be 61 to 90. I don't see that it says. In any case, the black line are 20th century observations. So this is the instrumented record for 100 years up to the year 2000. And then these different color lines represent different scenarios of how society, how global society will respond to climate change. So A2 in the red is known as business as usual. If we don't change anything and we continue pumping out our carbon pollution and changing land use, then we'll follow this red line trajectory, which at the end is the highest amount of warming. And we see that that takes us out to about 3.5 degrees by the year 2100. That's known as the business as usual scenario. You will see this term often. Okay. Then there are these other scenarios in green and blue, A1B or B1, and these are different combinations of the countries of the world doing things like ramping up their economies and or incorporating more renewable technologies and or how global population stabilizes, if it's going to stabilize at 9 billion as some forecasts envision. And so you'll see that the green and blue lines do not follow the red line because we're doing some things better. Now, if we took the year 2000 concentrations and we just clamped them there, then that gives us the pink line and what the concentrations would look like in that case. So these 4 colored lines here, the red, green, blue, and pink, are all generated by GCMs, global climate models, general circulation models, that take information about how the atmosphere works and how humans contribute to the composition of the atmosphere, and then generate 4 different pathways, these 4 lines, based on that information being incorporated into the computer models. These bars here, these vertical bars, indicate the uncertainty in these projections. So they're basically the error bars for these, meaning that even though the red line comes out at 3.5 degrees, it could be as much as 5.25 degrees or as little as 1.8 degrees. So it's going to be, the idea is it's somewhere in this region with the median being right there. So that's a functional graph that shows the outcome of some property, in this case, the temperature of the global surface. GCMs can also output these kinds of graphic map, spatially explicit projections, many of which we've seen already. So you've already had a sense of that. So the colored maps that we continually see in this class are often the product of some kind of climate modeling exercise that was geared towards asking some kind of a question about temperature, rainfall, or humidity, or wildfire, or flooding, or what have you. Any questions from those of you sitting here? Okay. All right, so how do they work? Well, we take the climate system and everything that we understand about the climate system, which is, we glossed over it very, very quickly in the first lecture or two. Everything we know about that and incorporate it into some mathematical relationships. So what do we know that we've talked about? Well, we know that water evaporates, and that's a solar-powered thing. So incoming solar energy causes water to evaporate, and clouds move. And so we've got air moving, water vapor moving. They contain energy, heat energy, and they have mass, which means they have momentum. And the Hadley cycle is one form of the water cycle, moving water and energy, heat content around the surface of the earth. And that the water is deposited in places in the form of snow and liquid rain. We know that the tops of clouds reflect sunlight. We know that ice surfaces, particularly in the Arctic, reflect sunlight, and on Greenland and Antarctica. And we know that there's a thin scum of green stuff on the surface that takes up CO2 and gives off CO2. And the nature of that stuff is being changed by a puny but persistent organism that has spread around the earth. So we take what we know about all of this stuff and we turn it into mathematical representations. Okay. And so we start with the fundamental laws of some of the fundamental laws of physics, such as the conservation of mass, the first law of thermodynamics, and Newton's second law. And you don't have to bother writing these down because, as you can see in the green box, it says you don't need to memorize these equations, right? We take these things, plus information about water vapor, and what we know about the structure and function and chemical composition of the atmosphere. We take all of this stuff, and we turn it into equations as best as we can. And we take these equations and we use them to describe how energy and mass move around the surface of the earth, how they interact with the biosphere, how they interact with the surface of the ocean. These notes will be posted as PDFs. They take all of this information and they apply it to a box of air. And we'll talk about how that works in a moment. So they divide the earth up into a whole bunch of grid cells, which means basically boxes. And each box is described by these laws of physics plus the information that we have about water vapor and how the atmosphere is structured and how it's operated. Now, as a reminder, conservation of mass is that the total mass of the system stays constant. So that, in this case, means the global climate system, the atmosphere and its interactions with the ocean and land surface. The first law of thermodynamics says that total energy stays constant and energy is transformed, but it's not created or destroyed. And that's really important because these grid boxes are going to exchange energy according to number 2, and mass, like water vapor and air molecule, are the various kinds of molecules in the atmosphere, according to item number 1 here. And things are going to move around. And we know that because the Earth is a solar-powered water cycle machine. That's what our weather's all about. And so the acceleration of water vapor and all the molecules that make up air is going to behave according to Newtonian mechanics and that acceleration is a function of force divided by mass. So the movement of air masses and water vapor, movement of clouds, all behave according to these properties. Okay. And we apply these things, like I said, to a grid box. So here is a portrayal of a handful of grid boxes. So we take the Earth down here, down below, and we lay a grid across it, latitude and longitude, basically. And then we apply that grid up through the atmosphere. And it's a three-dimensional grid, and you can see how that's drawn here. So down here at the surface, there are these sort of thinner layers of boxes. And then on top of that, you don't really see the three-dimensional individual boxes. Well, you can see one here. So here's this corner box. Okay, so there's going to be incoming sunlight that's traveling through some of these boxes, and each box has all of these equations describing what goes into and out of the box, and you can see that portrayed with these arrows. So all the exchanges with neighboring boxes, neighboring grid cells, are defined by those physical equations that we just introduced. And so they describe solar radiation traveling through the atmosphere and being absorbed by the surface, warming up the surface, causing the water cycle to operate. And then, of course, there's a certain amount of radiation that goes back out into space as part of the planetary energy budget that we described several lectures ago. And so all of these grid boxes are basically mathematically communicating with their neighbors. And over a series of billions and billions and billions of computations, you finally arrive at a convergent solution which portrays that for, say, 100 years from now, what the temperature of the surface will look like, or what the rainfall patterns will look like. Here's another portrayal of that. There are a bunch of different climate models that are out there. One of them is known as the Hadley Center Third Coupled Model. They have sort of these code names, HAD CM3, so Hadley, that's like the Hadley cell. So in the United Kingdom, their main climate research center is called the Hadley Center for Climate and Atmospheric Research or something like that. So the Hadley Center Third Coupled Model. So a coupled model means that the atmosphere and the ocean are interacting with one another mathematically through those processes we just described. So we said in the previous slide, we showed that there were boxes reaching up into the atmosphere. And notice in this particular example, the Hadley Third Coupled Model, known as HAD CM3, has many boxes reaching up 30 kilometers into the atmosphere. And they are 2.5 degrees in latitude in the north-south direction, and 3.75 degrees east in the east-west longitude direction. Then likewise, there's a series of layers that go down into the ocean. And so those equations are describing things like current, salinity, temperature, and oxygen content, all of which interact in the physics of the ocean and how it transports heat in the water. So when it says it's coupled, it means that the atmosphere is coupled to the ocean. And virtually all climate models are coupled these days. Way back in the old days when the computers were not very powerful, that was not the case. But you can see how this climate model views the planet. So it's not a very high resolution spatial portrayal. Nevertheless, the limitations to these things are largely based on computer power and the ability to do billions and billions and billions of simultaneous computations. So it's some of the biggest computers in the world that run these kinds of models, biggest and most powerful. We'll see a photo of one in a bit. There's maybe 24 of these different climate models around the world built by different research groups. Some of them are federal laboratory efforts. Some of them are university research laboratory efforts. They all tend to have models that are built differently. And I sometimes use the analogy of automobiles. So cars all basically get us from point A to point B, but they look different. And if you compare, say, a VW Beetle with a Tesla, you could open the hood and look at the engine, and they look very different, but they still both get you from A to B. Okay, so the climate models get you from A to B in terms of better understanding of how things work or generating scenarios of the future, but the different models of the climates, the different climate models act like the different car models. They look and function differently under the hood, but they give you basically the same kinds of outputs, or maybe not. We mentioned in that prior graph that the resolution was not very good. However, this has improved over time. Here are 4 different versions of the spatially explicit climate models. The FAR, SAR, TAR, and AR4 refer to the various different IPCC major reports on the state of climate change. So the IPCC is the Intergovernmental Panel on Climate Change. We'll talk about them quite a bit later in the quarter. But these are the first, second, third assessment reports, AR for assessment reports, and then assessment report 4. They could have used F for fourth, but then that would have confused with the first assessment report. In any case, you can see that the grid cells are 500 kilometers on a side for the first assessment report, 250, 180, and 110 in the assessment report 4. So that's a roughly five-fold improvement in the resolution. And if you compare these models, the Alps are portrayed as a slightly taller Lego block in the first assessment report, whereas there's quite a bit more resolution in the topography and the coastlines of Europe in the assessment report 4. So the computing power that's required increases as a function of the cube of horizontal resolution. So the more detail that you pack into what you ask the model to do, the more computer power it takes. And it's not a linear function, it's a cubic power function. So the past several decades have seen tremendous increases in computing power. It's been fascinating to see. We kind of take it for granted nowadays that what our laptops and our phones could do would take a room full of processors 20 years ago or 30 years ago. In any case, the limits of what our climate models can do in terms of how much precision that they can ascribe to a scenario, say for 50 or 100 years ago, that precision and accuracy in the computer model outputs is largely limited by computing power. It's limited a little bit by our knowledge of the physics of the atmosphere. And I've mentioned before that clouds and aerosols are things that climate models still grapple with. If you're interested in a career in meteorology or climatology or oceanography, modeling of clouds and aerosols is a way to go. Okay, so resolution has followed this historic increase in computing power that we've seen in recent decades. Okay, this graphic portrays several different things that we've pointed out a little bit, but that are all kind of the outcomes of computer models, and kind of the way that we use computer models in this class, which is to look at future scenarios or outputs. Notice I try to avoid the term predictions, because if you use that word prediction, it's kind of a loaded term that politicians and the public kind of perceive as locked in. That some climate modelers have found that if you use the word prediction, then people hang a lot of expectations on that. And really what computer models generate are different potential outcomes, different scenarios, possibilities. And it's really ours to see how closely these models play out in reality compared to these scenarios. But in some of these scenarios, we have a tremendous amount of confidence, others not so much. And that level of confidence is a function of how well we understand those particular phenomena. So for this graph, let's take a look. That this is a familiar kind of graph. We have time on the x-axis. We have a temperature anomaly on the y-axis. It's well labeled because it tells us that the reference is the period from 1980 to 1999. We see the zero line, and we see some colored lines here. We note that, well, notice the date when this was done. It was done long ago enough that it's now, even the forecast is historic. In any case, in the year 2000, this modeling exercise was conducted in which the model was operated and then compared to actual data. And actually we see 3 different models here. One of the versions of the Hadley model, the National Center for the National Climatic Data Center model, and then the Goddard Institute temperature model in the blue, orange, and red. And we see that for the most part, those 3 lines follow themselves quite closely. And they follow little ups and downs in the Earth temperature record compared to that 1980 to 1999 baseline. And then they forecast into the future, in this particular case, about 12 years. And again, those models follow one another in the blue, orange, and red fairly well. And then we have this other line in black. Okay, we look up here, IPCC ensemble. All right, so IPCC, we just identified what that is, Intergovernmental Panel on Climate Change. Ensemble. The ensemble is when everybody brings their model to the same place and they all use the same data and they compare how their models operate under the same conditions. It's like kind of bringing all the cars together and see how they compare. And then the white line is the 95% confidence interval. So this is essentially the interval, or sorry, the range of error. So in most cases, so the black line shows the output when you, essentially the average of a whole bunch of climate models in the black line, and then the white is basically the error bars, or that if you ran this model many, many, many times, 95% of the time, that black line is going to fall somewhere within that white shaded region. Okay? So it's like an error bar, but that's another way of thinking about it, is that 95% of the time, the black line is going to come out through there. Okay. So we note that this ensemble is another way of using models, which is to run a bunch of different models all together at the same time with the same boundary conditions. That is the information you put into the model to begin with. Let the models run and compare their outputs, compare the scenarios that they generate. And notice that for the most part, the ensemble runs are pretty close to the individual runs done by the Hadley, NCDC, and Goddard models. Okay, so we've seen in this quarter, and we will continue to see several different examples of these kinds of GCM outputs. Here's the Earth simulator. This is one of these supercomputers, crazy supercomputers. I think this one is at the National Center for Atmospheric Research in Boulder, Colorado. Many processors. You can imagine the amount of heat or the amount of electricity it takes to run this, the amount of heat that it puts out, and then the amount of fossil fuels required to keep this thing cool. Now there are some things, as I mentioned earlier, clouds are often a stumbling point in climate models, because the size of a cloud, even these giant thunderstorms, can be a few kilometers across, but they're not the same size as a grid cell typically. And as a result, they are not simulated very well by these large scale climate models. So what you can do is you can take these global models and you can squish them down, and you can say, ignore all the rest of the world. I'm just going to focus on the center of the United States, for example. And this is something called downscaling, and it provides us with a way to focus in and increase the resolution of the climate models. In that case, the clouds become better, but they're still rather elusive because they move around quickly and they change fast in terms of their energy content and their water content. Okay. So what I want to do here is to switch over to this website for CalAdapt. And that's right here. So CalAdapt is put together by the state of California to be a resource, very useful resource actually, once you start poking around in here. And one of the reasons that I bring it up is that we can come back to it later in the quarter, but it's also a great resource if you're ever taking any other classes where you want to write a paper, or if you need information about how climate may change in California, then this is your go-to place that will provide you with that kind of information, or at least with linkages to other places where you can find useful info. Okay, so let me just begin a little tour here by scrolling down, and there, of course, in the background, some of our iconic California mountains, Half Dome and Yosemite. Okay. So they have various tools on here that are quite useful for generating graphics and stuff, many of which you can download. So there's these climate tools. You can download data and find resources, and we'll explore those in a moment. If you are a programmer, if you create apps, there are ways to utilize the resources at this site in the apps that you're building. There's various contributors. Let's go up to the top here. Notice tools, data, resources, blog about help. We won't bother with those right now. Tools, let's see what we've got for tools. Climate tools. So these products are scenarios from climate models. In some cases, there will be data that are portrayed that are historic data. And in some cases, there are data that are future scenarios. And so what we notice here is that there is different nomenclature utilized for the future emissions pathways. So in the graph with the business as usual that I showed a few minutes ago, that was kind of an old-fashioned way of describing what the future scenarios of population, technology, and economics will do for greenhouse gas emissions. A couple of years ago, they changed that into these things called the RCP, the Representative Concentration Pathway. There are different RCPs. You see one here, it says 4.5. There's another RCP, 8.5. And the number 4.5 or 8.5 refers to how much radiative forcing humans will impose on the atmosphere. So this is a future with an extra 4.5 watts per meter squared of greenhouse gases and other effects on the atmospheric temperature. And this is a scenario, this is basically the business as usual scenario, the 8.5 watts per meter squared of extra warming in the planetary energy budget, in the atmosphere. So this first one is kind of a better scenario, because if you read here, it says, this is a climate future in which emissions peak around 2040 and then decline. Okay? So that's good. That's doing the things that we want to do. That's a pathway that California is on, 100% renewables. Okay, at that level, we'll still get about 4.5 watts per meter squared of radiative forcing. But if we continue business as usual, so we let the greenhouse gases rise throughout the 21st century, then we're going to get an RCP or a warming of 8.5, and the RCP refers to what the line looks like. That's a representative concentration pathway, greenhouse gas concentrations that lead to 8.5 watts per meter squared of radiative forcing, which would lead to maybe 3.5, or no, that's probably more like the 5.5 degree warming scenario. So then you can look at, well, what might happen to California's climate in terms of these kinds of scenarios. So let's just go and we'll click on one of these ones. Annual averages. You click on that and you can look at different characteristics: maximum temperature, minimum temperature, and precipitation. And you can click on either of these boxes, takes a second, and flip from one scenario to the other. Okay. You can go to this. So what it shows here is a graphic of maximum temperature in degrees Fahrenheit going out through time. And let me zoom out a little bit to help see it all in one view. So we're looking at maximum temperature going out through time. So these are the climate model scenarios, and you can see which models are being portrayed based on the color codes here. So these are historic data, okay, and then these are the data going forwards. Okay, and the location is for Sacramento, our state capital, that's shown in this map here. You can change location by clicking on where it says change location, and you can do it a bunch of different ways. You can, you're supposed to be able to do this. Let's see, I think you can do this by map. Or you can upload a map. Oh, here we are, duh. Okay. So, let's go to, let's put it on the campus. Okay. Is that right? The campus is kind of there. Oh, we'll just put it on Santa Cruz. Okay. So now the grid cell is that one we just highlighted, and notice the size of the grid cell for this climate modeling exercise is, I'll zoom in, is basically, darn it, right here, Santa Cruz, the west side, downtown, part of campus, not quite up to Scotts Valley or any place like that, okay? So that's climate model output for that grid cell from these models. Again, let me zoom out. Here's an interesting feature that the historic annual mean from 1961 to 1990 was 69.4 Fahrenheit, and that will be about 4 degrees warmer by the period of time 2070 to 2099. Okay, all of these data are extracted from climate models. So that's the good scenario. Okay, emissions peak around 2040, then decline, RCP 4.5. So let's flip over to the not so good scenario, and now we see that the historic annual mean goes from 69.4 to 76. So it was 4 degrees under RCP 4.5, and under this scenario, it's more like 6.5 degrees of warming. What about for minimum temperature? In many cases, it's nighttime temperatures that will warm up more than daytime temperatures in some locations of the world. So under RCP 4.5, Santa Cruz will go about 5 degrees warmer at nighttime, averaged over the year. That's, well, we'll just round off. We'll say that's 45, so that's 5 degrees under 4.5. And 8 degrees warmer at night under RCP 8.5. Let's look at what the climate models say for Santa Cruz for precipitation under RCP 4.5. Okay, notice, what do you notice about the graph here? Anyone? Very erratic. Is it going up or down? Very hard to tell. Not really, right? It looks pretty horizontal. I think if you squint your eyes and try and draw a line, imaginary line through that, I think it looks pretty horizontal. It's certainly not going wildly up, nor is it going dramatically downward, right? It may be getting more erratic. That's certainly a question. This is the 4.5, RCP 4.5 scenario. And what we find for California, at least for some parts of coastal California, is that the average amount of rainfall averaged over many years is thought to not change. However, the variability from year to year may in fact change quite a bit. And that sounds somewhat consistent with recent years here, where things have been quite dry with the notable exception of winter 2017. Okay, so what's this? This is 31.5 to 35.5. So that's a 4-inch difference. It kills me to not use metric here, but oh well. Under the 8.5 degree scenario, it now begins, the 8.5 watts per meter squared scenario, it now begins to look like, at least some of the models seem to suggest that maybe there is a bit of an upswing, certainly more variability. And now we see that that may be as much as 8.5 inches more rainfall in the winters or over the year here in the future. Okay. So that was a possibility under tools, and you can see that there's lots to explore under here. So for example, wildfire. Okay. course, there's a tremendous amount of concern about the wildfire based on recent events in the past few years, some very dramatic wildfire. So we have scenarios of baseline wildfire and modeled wildfire into the future. So notice you can change a few different things here. Annual area burned averaged over 10 years. You can change it, or 5 years. We'll just leave that on 10. Now, what model do you want to have do this? There are 4 different options. There's a hotter, drier model, a cooler, wetter model, sort of the average, and this MyRock model, complementary one that's, I think, actually quite wet. So let's go with the hotter, drier one here. And we're gonna make it the worst case scenario. And the population growth, we'll call it high population growth. So that means lots of people on the land, lots of houses, lots of building, lots of land usage. Okay, so we're starting here in the year 1960, and we're gonna watch how, so this is hectares of annual area burned. Okay, and you can play the animation if it works. So it's going up by decades, and you can see we're now in 2030, 40, 2050, 2060, 70, 80, 90. So I'll stop those. You actually also typically grab these things and pull them out. So by 2090, you can see tremendous area burned averaged over the 10-year period throughout the Sierra and the southern Cascades, the Siskiyous, some of the transverse ranges, coastal mountains. Notice even up here around southern San Francisco. See what's out there in data. So you can actually, if you're doing a project in another class, you can come and get data that's coded for spatially explicit outputs for drawing maps, for example, or data for use in applications. You see there's an API button. And so these are data that are useful for running your own analyses or drawing your own maps. If many of our students in environmental studies take the GIS class, Geographic Information Systems, which is a way of using the information from maps and spatially explicit data to understand better environmental problems and to conduct environmental problem solving. A very popular class, highly recommend it. There are other resources here that can help you with using climate data or finding your own climate data elsewhere. So this is a very useful site. Okay. I'm gonna take a second here and switch over to the other half of this morning's lecture. There we go. Okay. Okay, so what I want to do now is to segue into extreme events. Because extreme events are important in this discussion of climate change impacts. Because extreme events are in some cases likely tied to climate change. In some cases, our understanding of how extreme events may be tied to climate change is not very well understood. However, it's extreme events that are often perceived by the public as signs that climate change is happening. In particular, Hurricane Katrina in 2005 appeared to be a bellwether moment in American society in which many people seem to understand that climate change is real and that it's happening. And for them, Hurricane Katrina was that moment that showed them, that convinced them that climate change is real, although it's still very difficult to pinpoint the cause of any one storm as being from climate change. We're going to talk about extreme events in the remaining period of time. So we're just talking about GCMs that create scenarios like this one that can take observed data, observations, and synthesize them into trends. This one here showing the warming that occurred from 1976 to the end of the 20th century. And you could note that almost everywhere are brown circles indicating warming. Here's our little color-coded key down here. Blue circles indicate cooling, and you notice that there's not a whole lot of cooling in many places, a few ocean surface locations, but certainly over land, it's virtually all warming. Particularly in the northern hemisphere, the size of the circles indicate the amount of warming, and the amount of warming seems to be greatest there. And note that this begins in 1976, and there are many indicators that suggest that there was something that happened in 1976. Often that's a tipping point in climate historic data where we start to see pronounced warming begin. Likewise, GCMs can show us that precipitation trends have occurred. Precipitation has trended upwards in many places and downwards in others, such as sub-Saharan Africa, parts of Asia and the Southwest, and South America. These are all slow chronic changes, slow creeping changes that we don't detect on our sort of day-to-day basis. It's the extreme events that we tend to notice. Okay. Land areas are warming more than the oceans, and the greatest warming is occurring at high latitudes. So this GCM output is a forecast for the future. And we see the baseline down here at the bottom is relative to 1990. And this is annual mean temperature change for that 30-year period at the end of this century. We see that the warmer or more orange colors are all in the northern hemisphere, and particularly at the extreme northern hemisphere. And that average globally, the warming's about 3.1 degrees in 2085, as envisioned by this particular model output. Okay. Some areas are going to become wetter and others drier, with a slightly overall increase in global precipitation. And that makes sense because if you warm the atmosphere, you should cause more evaporation. If you warm the global atmosphere altogether, then you should create a greater amount of evaporation overall. That just makes sense. Okay. This is also a GCM scenario of the future. But what is an extreme? Okay, so let's just stop and think about that. So the extremes that organisms, whether they're in a tropical forest or Arctic tundra or a farm field in Iowa, the things that are usually most important are the extremes of temperature or the extremes of precipitation. So let's think about the extremes of temperature. So here we have this graphic in which we have across the x-axis is a range of temperatures, a continuous range of temperatures. Maybe they didn't label it this way, but it could be like minus 40 to plus 40 or minus 10 to plus 30 or something like that. On the y-axis, you can see it says probability of occurrence. How likely will that particular temperature occur? And at any particular place on the Earth, you're going to have an average temperature, which in Santa Cruz is probably about 50 Fahrenheit, I'm guessing, maybe in the high 40s. That's average, annual average, taking the highs and lows of the winter and summers into account. But the temperature is going to be somewhere around the average. Now, on rare occasions, you will have some heat waves. They don't happen very frequently. They have a low likelihood or probability. And on rare occasions, you will also have these low temperature events or cold temperature extremes. Cold snaps, they're sometimes called. Cold snap is sort of the common term that's sort of analogous to heat wave. They're important for farmers, especially with sensitive crops. Okay, so you can see that they occupy the tails of this distribution. This distribution is the normal distribution, also the bell-shaped distribution, the bell curve. Okay. So we can easily ascribe a mathematical description for these two tails of the probability distribution. So these might be two standard deviations from the average. So you can mathematically define it that way. So you can say, what is an extreme? Well, it's whenever the temperatures are two standard deviations above the mean or the average. So there's a functional definition that we can give to an extreme like that. For precipitation, the distribution of events is different. So light rainfall events, little drizzly things, are way more common for almost everywhere on Earth. Small rainfall events are more common than the really heavy deluges. Okay, we see that pretty much everywhere. So the extremes of precipitation are going to be when you get heavy rainfall events way out here on this far tail of this distribution. Okay. Now, of course, the other precipitation extreme is way down here. It's not labeled, but it's zero precipitation for extended periods of time, drought. Okay. So we can define these things mathematically or operationally, like in terms of drought, when you have no rainfall for a certain amount of days or months. Okay. So let's think about examples of extreme events that we're probably all familiar with, but maybe not so much. Okay. So the kinds of things that are going to be important globally as a consequence of climate change are droughts and floods. So ramping up that water cycle is going to mean some places are going to get a whole lot wetter. Other places are going to get drier. It's going to be very location specific. But these are two of the primary outcomes of extreme events that will be a consequence of climate change. Some of the extreme events come about from very complex series of events or complex physical features coming together or interactions with the biosphere. And so wildfires, of course, a very important impact here in California and throughout the arid and semi-arid Western US. increasingly so in Western Canada and many other parts of the world. So wildfires, of course, driven by fuel, driven by weather conditions, driven by extreme winds, particularly in California, dry vegetation, which themselves, all of those things have climatic connections or weather connections. Then there's a complicating factor of land management there as well. Smokey Bear has been telling us to put out all of our forest fires, which has allowed a lot of vegetation to accumulate, which would have, in pre-contact times, would have been burned off by periodic wildfires. So land management over the past 100 years or so has contributed to wildfire extremity by altering the wildfire frequency. Killing freezes that may be counterintuitive to a story about climate change and global warming, but with changes in the way that the jet streams are meandering around the Earth, we often see widely amplified variations in the jet stream, which allow things like the polar vortex to have an impact on weather in the eastern part of North America. You may have heard of this term from weather forecasts and stories on the Weather Channel a couple winters ago, where those wild fluctuations of the boundary between the Hadley cycle and the Ferrel cycle and the polar cycle become highly amplified. That means whereas they used to meander in a sort of a moderate manner, they are now meandering much more radically, allowing for cold air from the Arctic to travel southwards in some of those meandering portions of the jet stream, leading to those events that are blamed on the polar vortex. There are tropical storms, cyclones, and hurricanes that are driven by sea surface temperature. If you warm up the sea surface because you've warmed up the atmosphere, then you might expect to ramp up the frequency or intensity of these kinds of major storms that are all fed by sea surface temperature that creates energy and water mass that is entrained in these storms that flood over here on the right. I forget which hurricane this is. This was last year, taken from the space station, or 2 years ago. Tornadoes are extreme events. However, there's no evidence right now that there is any change in tornadoes associated with climate change. Perhaps surprisingly, given how storminess is sort of an expected outcome of climate change. Heat waves and cold snaps, as I just mentioned, with intensification of the jet stream turbulence, it is leading to greater heat waves and these incursions of cold air. I guess killing freezes and cold snaps are kind of the same one now, I just realized. Gonna have to kill one of those. Related are blizzards and ice storms. Again, these seem counterintuitive in a warming world, but the weather at any one place, weird as it may be, is being countermanded by extremely hot temperatures somewhere on the planet. So sometimes you may have seen these images of congressmen throwing snowballs because of a snowstorm in April in Washington, D.C., using that kind of imagery to suggest how can there be global warming when we have a snowstorm in Washington in April? Well, weirder weather is a prime example of extreme events resulting from climate change. Not everything is about stuff getting hotter. You can have weird storms occurring, and as we already mentioned, you can have cold air traveling from the Arctic as the jet streams become more meandering. Strong wind events, such as the kinds of wind patterns we get in California, the Santa Ana or Diablo winds here in the North Bay region, or sorry, in the San Francisco Bay region, similar winds that travel off of our adjacent deserts and are very dry and strong, and that tend to be really problematic for fire risk. And dust storms in many places in the world where agricultural practices have led to large areas of ground, of soil being disrupted, dust storms resulting from climate change, resulting in tremendous amounts of soil erosion. So these are all examples of extreme events, some of which may or may not be getting more extreme or more frequent as a consequence of climate change. How might some of these things work? Okay, so there's usually a complex pattern between things like the sea surface temperatures and evaporation that puts moisture in the atmosphere above the water adjacent to land. Changes in air currents, weather patterns, wind directions, where the wind normally blows from. A warmer atmosphere and increased moisture in the atmosphere. These are the recipe for greater moisture and heat energy in the atmosphere, greater storminess. Okay. So these things kind of all add up. Greater, warmer atmosphere means more energy, more moisture means more stuff for the energy to move around. That translates into more powerful storms. There's a combination of several factors that leads to this greater storminess. Heat waves that we mentioned are a prime type of extreme event that's expected to become more common. This has important impacts on human health. We'll talk more about this in a week or two when we get to impacts on human health. Here's an example. I believe this one is in Chicago. We're looking at a timeline here of 2000 and a heat wave event in 2003 in red by comparison to a similar period of average time between 1999 and 2002 portrayed in blue. On the y-axis is daily mortality, number of deaths. That's the bars. On that was on the left-hand axis. On the right-hand axis is temperature. And I don't know how well you can see it. It goes from 0 Celsius to 35 Celsius. So 30 Celsius is in the upper 80s Fahrenheit. And temperature is portrayed by these lines. So the blue line shows the mean daily summer temperature between 1999 and 2002. So it's hovering around 20 Celsius. So that's 20 Celsius is roughly 68 Fahrenheit. Okay, so that's pretty moderate. Like I said, I believe this is Chicago, where it's also very humid by the Great Lakes. And as a result, hotter days are more humid and more uncomfortable. And so here we see a couple of heat waves in the year 2003. We see temperatures that are 5 or to 7 degrees warmer or more than the average of the previous decade. We see several times when the temperature goes quite a bit above, so 10 degrees above the prior average. And notice this is persistent for a few days. August 4th, right here, August 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th. So that's like a 10-day heat wave. And when it's hot and humid, it often doesn't cool down all that much at nighttime. It's one of the things that's different out here. You know, right now the temperature in my backyard is going down into the 30s during the night, pretty chilly, and up into the upper 70s during the day. So a tremendous daytime temperature difference, day to nighttime temperature difference. When it's humid on the eastern half of the US, you don't get that kind of fluctuation. The nighttime temperature stays pretty hot, pretty warm. And notice, so the bars down here, the red and blue bars show the number of deaths, the mortality in the city. And there's about, what is that saying? About 50 people at this line. That's sort of the background, 50 people a day. Then this heat wave right here hits, and you can see that the number of deaths double initially for the first few days, and then they go up to like 300 people on this particular day here by about day 10 of the heat wave. And that's just because people, this is particularly stressful for the elderly or for people who have pre-existing conditions like asthma or other health issues. They're immunocompromised, their immune systems are already battling illnesses. And the heat wave is yet one more thing that is very, very stressful. Heat waves are also stressful for crops and for cattle and other livestock. You got to expend water for air conditioning. So that's fossil fuel use. You've got air conditioning is fossil fuel use. You have to use water for animals to drink or to cool animals down during these events. And crops can suffer as well from water loss during heat waves. We mentioned wildfire, which of course here in California is going to be an ongoing concern for years to come, between the combinations of land management, vegetation growth during exceedingly wet years, and vegetation drying during drought years. Fertilization of that vegetation growth by extra CO2 in the atmosphere. Fertilization of the vegetation growth from tailpipe nitrogen emissions, N2O. Some of that N2O comes back down to the ground and it gets into the soil and acts like fertilizer in some cases. You can see that with rising temperatures and reductions in humidity, going hand in hand with increases in wind, as you know, that's the recipe for problems with major wildfires. You can see this trend graph on the bottom. This is 1970, 80, 1990, and 2000. And this is the number of major wildfires. Okay, 21, 9, 36, 122 in the year 2000. Now, in some cases, there may be a reduction in extremes that actually leads to ecological consequences. And so here's an example of this little insect. This is a beetle, and it's called a bark beetle. And you can get a sense of its size because it's standing on this match head, and it's pretty tiny compared to the match head. But this bark beetle is responsible for destroying vast areas of western forests. Eastern forests as well. But more recently, it's become a real problem in parts of British Columbia and Alberta in Canada. And you may have seen in the news over the past few years that they are suffering from drought and these beetles, and that's leading to problems with wildfire. So the reduction in some extremes might lead to an increase in other extremes because you've got all these beetle-killed trees on the landscape that are dead and just standing around waiting to burn. And what they do is that when a tree is stressed by drought, the tree has a hard time making chemicals that can fight off infection by beetles. The beetles get under the bark and they make these little tunnels. And the tunnels are where they lay their eggs and where they eat the tree materials. And what they do is they block off the ability of the tree to send sugars down to the roots. And so basically the roots die off, they starve. The roots are starved because they no longer have a source of food energy, those sugars. And then the tree slowly dies because the roots are no longer functional. The tree was already pretty stressed out from drought to begin with. And what happens is that the low temperatures in winter that used to kill these bark beetles don't happen as often anymore. These are also called pine beetles. Pine beetles or pine bark beetles. Bark beetles. They live under the bark of the tree. So it used to be that every once in a while it would be as cold as -40 Celsius, which I mentioned before is also -40 Fahrenheit. Little bit of trivia there. Anyways, -40 Celsius is a temperature that, that kills the larvae of these pine beetles. And back in the day, this was effective at keeping pine beetle populations under control. Now, those -40 Celsius temperatures, they still occur once in a while, but just not as frequently. So they are not as important as a abiotic control on pine beetle populations. So the pine beetles can thrive and flourish and their populations go way up. And so the trees are stressed by drought from climate change. The beetles come along, they're actually benefiting, if you will, from climate change. Their populations are soaring because of a lack of cold temperatures. And so the trees are hit with a double whammy of drought and pine beetles. Turns out the pine beetles also carry around some fungus that they eat in the tunnels. And that fungus carries around a disease organism that also affects the trees. So it's actually a triple whammy that the trees are faced with. So there are large regions of British Columbia, as I mentioned, that are being affected by a major pine beetle outbreak. You can see in the shaded region here. And portions of the Rockies and the Sierra and the Cascades also affected by different species of pine beetle or bark beetles, shown in the orange in the graphic on the right-hand side. I have a friend I grew up with who lives about 10 miles from Nelson, BC, and he is a forest firefighter, and he used to have winters off, but that's no longer the case nowadays in British Columbia. So how might extremes change in the future? We had that bell-shaped distribution. And so now we see some examples here of how that bell-shaped distribution might change. So in these three scenarios, the previous climate is drawn in light gray. And so here's that temperature bell-shaped curve. Under the new climate, we get the black curve, which you can see in the upper graph has shifted towards the right, towards higher temperatures. The temperature scale is down at the bottom, cold on the left, average in the middle, hot on the right. So we see that there's a new average. It's moved over to the right towards warmer temperatures. We see less cold weather in a situation like this. And we see more hot weather in the pink, and even more record hot weather in the extreme, in the red extreme tail of that distribution. So more warmth, less cold. Now, another possibility, so that first one is an increase in the average temperature. That's when the entire curve just stays the same shape, but shifts towards the right, towards warmer temperatures. Another possibility is that the average stays the same, but the variance or the stretch of that bell-shaped curve increases. Okay, so an increase in temperature variance. So in this case, you get more variability both in terms of cold events and warm events. So you can see that here, more cold weather, more hot weather. Now, another possibility is that you might get a combination of these two, where you get an increase in the average and an increase in the variance. This is probably the more likely scenario in which we see that the curve shifts towards the right and it kind of flattens out. So we get a little bit of change in the cold extremes, and we get a lot of change in the warm and hot extremes. And it's this bottom scenario that seems to be the situation that's playing out. More variability and a shift towards warmer averages. Okay, I'm not going to go through this entire list, but this is an important list for the class because these are examples of the ways that various kinds of extreme weather events are projected to increase. Okay, the way that they will change during this century is highlighted on the left-hand side in the dark blue notes, bullet points. The impacts or the consequences are shown here on the right-hand side in black. So for example, the very first one, higher maximum temperatures, more hot days and heat waves over nearly all land areas. And notice it says in italics, very likely. Okay, so the stuff that's in italics for each of these projected changes on the left is the confidence with which the Intergovernmental Panel on Climate Change views this statement. Okay, so these changes, higher max temperatures, more hot days and heat waves over nearly all land areas, this is very likely to happen. That's already happening, frankly. Okay, so confidence is pretty high in these first three, in fact, a little bit less so for the last two bullet points. But back to this one, higher max temperatures, more hot days and heat waves. What are some of the impacts? Increased mortality for the elderly and the chronically ill in urban areas. And we saw that from the heat waves in Chicago example. Damage to crops, heat stress on livestock. Okay. Less cold temperatures, changes in precipitation, more intense precipitation, greater drying in other places, and the various impacts, okay? So make sure that you read through those and you understand why those impacts or consequences go along with the projected changes. Okay. What about the costs that come from this? Well, if you take this interesting scenario here, we see the number of events from some kind of disaster all the way up to 450 per year over time. So on the x-axis, it starts in 1900, goes to 2000. So this is the 20th century. And we see that the various kinds of disasters, drought, earthquake, extreme temperature, famine, flood, insects, landslides, volcanoes, all kinds of stuff here, wildfires, windstorms. So they're going up tremendously, and they're going up partly as a consequence of population, partly as a consequence of technology that detects these things, partly as a consequence of communications, which allows us to report these things. Notice the trends in number of reported events. So one needs to keep in mind that when economic impacts are discussed, need to keep in mind the number of reported events. Plotted here is earthquakes because they are easily reported by automated technology. So if there were any increases that would be detected here, the increases here are because of the build out of the technology starting in the 1960s of seismometers around the world. And so this trend here is actually a reporting trend, not so much an increased trend in necessarily in earthquakes. But if we look at the actual dollar value of these weather extremes, then we see trends like this. On the x-axis is time from 1980 to 2008. So that's a 28-year period. On the y-axis on the left-hand side is the number of events each year, shown in the blue bars. And then on the y-axis on the right-hand side is the damage in billions of dollars. Okay. So that we have two different lines. The blue line is the amount in damages, economic dollar value at that time. And then the red line is the damages corrected to $2007, because you know inflation is always occurring, so that the value of a dollar changes with time. Okay, and so whenever you compare economic amounts or dollar amounts over time, it should be corrected to one particular year so that you can understand the basis for comparison. Okay, so we see various numbers of events, anywhere from 0 to 4 events, up through the mid-1990s. 1998, we had an El Nino. Here is 2001. What happens in 2005 to increase the amount of U.S. weather disasters? Anybody remember? I already mentioned it once. Yes, this is Hurricane Katrina, as well as others that occurred that same year, and that particularly Katrina, that went across Florida before it hit New Orleans and neighboring states. So the economic impact here was tremendous from one of those 5 events. So the economic impact of these extreme events can be disproportionate to the number of events. Okay, so just for 1 year, as one example, we're running out of time. Here's major climatic and weather events in 2012, just in just 1 year, notable events that cost the U.S. economy, FEMA, lost time, wages, injuries, medical expenses to these weather and climate events. If we had time, we could talk more about hurricanes, because there's always a lot of attention around this time of year, because the hurricane season is just starting to wind down. We had a couple of big hurricanes this year, the one that hit the Carolinas, and then the one more recently, Hurricane Michael, that went from a tropical storm to a Category 4 hurricane virtually overnight. That was almost unheard of, that a storm could ramp up, accelerate like that in that period of time over very warm Gulf of Mexico waters. So their power is dependent upon sea surface temperature and the humidity above their sea surface temperature, and some kind of an initial disturbance, which for the hurricanes that cross the Atlantic is usually a dust storm that occurs off the Saharan desert. The dust provides the particles for the initial clouds to begin forming, and there's usually a low pressure region that's required, of course, that eventually becomes the eye. Since the ocean surface temperature of the world is warming, it would make sense that hurricanes might become more intense. We're going to have to leave it here for now, but the bottom line, I'll just sneak ahead to that. Oops, where was it? Is right here, is that there is a trend towards a greater number of the strongest storms. So you know that the hurricanes are often are categorized according to the Saffir-Simpson scale. If you watch the coverage on the Weather Channel, Category 4 I just mentioned a few minutes ago. It turns out that the bottom line of the hurricane research to date is that there's a greater number of Category 4s and 5s. The categories 1s, 2s, and 3s are staying about the same. But what we see is a greater number of 4s and 5s. And you can see the graphic here, numbers of 4s and 5s increasing dramatically over recent decades. Okay, I'm gonna stop here because I gotta shut this down and let it do its thing. And we'll see everybody back here next Tuesday morning. Thanks to the gigantic crowd that showed up this morning. We'll see you next week.